Okay, so our next continued talk is from Richard Shuai from Post Lab. He's a fourth-year PhD student, and he's going to talk about ensemble-conditioned protein sequence design with Caliby. Take it away.
Okay, hey everyone. Today I'm going to be talking about our method Caliby. So Caliby improves upon structure-conditioned protein sequence design by conditioning on structural ensembles. So our overall goal in structure-conditioned protein sequence design is, given an input backbone, we want to design a sequence that'll experimentally fold into our desired structure. So right now, for this task, protein MPNN is the most widely used model due to its proven experimental performance. And as you can see from this figure in their paper, basically, given an input target backbone, protein MPNN can be used to design a sequence onto this backbone, such that when you experimentally characterize this sequence, it'll fold into a structure that closely matches the desired backbone. But right now, while protein MPNN is very good with simpler and more idealized backbones, it still struggles a lot with a lot of these structurally complex backbones. So here we show some examples where we designed 512 sequences with protein MPNN, predicted each sequence with single sequence AlphaFold 2, and then took the best prediction. And you can see that even with 500 tries, protein MPNN still fails to find a sequence that is predicted to fold back into the target backbone. So this suggests that these backbones are still out of reach from design. So the natural question we can ask is how can we design better sequences? So we first want to note that natural sequences in our training data reflect more than just structural constraints. So because these sequences are actually obtained from extant organisms, then they'll naturally reflect things like phylogenetic relationships and neutral drift. Additionally, throughout evolution, they've not just been optimized for structural stability, but also just various functional constraints. And then finally, there's just some bias in the way that we choose to characterize certain sequences and structures in our data set. And so what happens is when you train sequence design models on this data, these models end up learning to reproduce these biases. And so to fix this, we actually just propose you can average predictions over a structural ensemble, and in this way you can isolate structural signal during sequence design. So hopefully this intuition helps kind of understand why we designed Caliby the way we did. So we trained Caliby to take in an input fixed backbone and predict a structure-conditioned POTS model. So to do this, we use an architecture very similar to the protein MPNN architecture, but instead of the last autoregressive decoding step to generate a sequence, we actually take the final layer node and edge embeddings to predict site-wise and pair-wise interaction terms of a POTS model. And so this is actually following very closely to the chroma design sequence design module. And so with this structure-conditioned POTS model, you can sample sequences. You can imagine you randomly initialize a sequence, then you perturb and you resample amino acids until you find a low energy or high probability sequence. And it turns out that even though Caliby is only trained on fixed backbones, the way we have it set up actually extends very naturally to ensemble-conditioned design. And so all you have to do for ensemble-conditioned design is just average the POTS models obtained from each structure in your ensemble. And so here we use synthetic structural ensembles. So to walk through it step by step, what we do is we start with an input backbone. We run partial diffusion with a backbone generative diffusion model. So in this case, we use Pappardelle 1C, and we generate a synthetic ensemble. And so for each structure in this ensemble, we'll run Caliby to generate a POTS model for each structure. And so now with all these POTS models, we can just average the POTS model parameters and get a single POTS model that is an ensemble-conditioned POTS model now. And now we can sample sequences from this POTS model in the same way. And so to kind of visualize what the sampling process might look like, as we said, once you have an ensemble-conditioned POTS model, all you have to do is randomly initialize a sequence and then resample amino acids until you find a low-energy sequence. So we average over synthetic structural ensembles because what we want to do is isolate structural constraints during sequence design. So to illustrate what I mean, you can kind of, for a given fixed backbone, you can visualize the energy landscape over the possible space of possible design sequences. And so here, a low energy sequence would mean that this sequence is a kind of a good and stable sequence for this backbone. And so when you run Caliby on a fixed backbone, it produces a POTS model that basically defines a energy landscape over the space of possible sequences for this backbone. And so here you can see that even though the prediction's pretty good, the minimum of the backbone is actually not, or sorry, the minimum of the prediction is not actually exactly where the true energy minimum is. But if actually what happens is if you run Caliby on each of the predictions, or sorry, each of the structures in this ensemble, visualized in gray, you can see that you have like these predictions that have some variance, but the key point is that they tend to agree where the structural constraints of the ensemble are satisfied. And so what we hope is that when you average these predictions together, visualized in orange, you would get an energy like a predicted energy landscape that much more closely matches the true energy landscape of your sequences. And so to test whether this approach actually works, the first thing we do is benchmark ensemble-conditioned Caliby against fixed backbone Caliby. And so here we use a test set of 189 native backbones. And we design sequences with either approach and use single sequence AlphaFold 2 to assess the designability of these. So on the left here, we have SCRMSD. So here below the line means that ensemble-conditioned Caliby outperforms fixed backbone Caliby. And on the right, we show PLDDT, which above the line means ensemble-conditioned Caliby outperforms fixed backbone Caliby. And as you can see, for most native backbones, ensemble-conditioned Caliby actually does provide a performance improvement over fixed backbone design. And so similarly, we bench against protein MPNN. And just like the last slide, we show SCRMSD on the left and PLDDT on the right, where below the line on the left means ensemble-conditioned Caliby is better than protein MPNN. And on the right, above the line means ensemble-conditioned Caliby is better than protein MPNN. And so as you can see, for almost every single challenging native backbone, ensemble-conditioned Caliby is able to find much more designable sequences than protein MPNN. And actually, interestingly, if you actually look at native sequence recovery, ensemble conditioning actually reduces native sequence recovery. And this is actually kind of expected because we believe that the sequences that come from ensemble conditioned design more closely reflect structural constraints now as opposed to evolutionary constraints. And so far in our analyses, we've been using single sequence AlphaFold 2. But we can actually interpolate between AlphaFold 2 with MSA on the left and single sequence AlphaFold 2 on the right. And we interpolate by basically gradually masking columns in the MSA to slowly reduce the amount of information provided by the MSA. And so with the dark orange line here, you can actually see that sequences from ensemble condition design rely less on coevolutionary information for accurate structure prediction. And so this actually kind of supports the idea that our sequences do have a more robust structural signal in them. And so this work was done in collaboration with Gina. Yeah, she's been super helpful with all of this. Also, with the help of Gina, we actually chose some sequences to actually experimentally test. So here I'm showing a filtered test set of native backbones. On the x-axis here, we have the best design out of 512 sequences from soluble MPNN. And on the y-axis, we have the best design out of only 16 Caliby sequences. And as you can see, even though soluble MPNN is given 32 times more tries than Caliby, there's still so many backbones that are completely, mostly undesignable by protein MPNN, but are much more designable under Caliby. And zooming in, we chose 12 of these sequences to test, with 2 of them being transmembrane proteins. And in general, when we tested these proteins, they tended to be well-folded and thermostable. And actually, the CD spectra tend to match, or do match the expected secondary structure that we see in our backbones. And we also can visualize one of the transmembrane proteins that we designed successfully. And yeah, this shows that we can solubilize transmembrane proteins as well. And yeah, and in total, 11 out of the 12 designs that we tested were successful, with the one failure being the other transmembrane protein, which actually did get a low AlphaFold 2 PLDT of around 65. So for main takeaways, we want to emphasize that protein structure data sets are biased and contain undesired correlations. So when you train models on these data sets, they inherit these biases for better or for worse. To rectify this for structure-conditioned sequence design, we propose an inference time approach that all you have to do is condition on synthetic ensembles to isolate structural constraints. With this approach, we show that we can design sequences for backbones that are previously undesignable with protein MPNN, and we have experimental validation to show this. And finally, beyond just synthetic structural ensembles, which we used here, we're hoping that we can actually use this exact same approach for any user-provided ensembles. And so we're hoping that this can be used maybe in the future for multi-state design. And yeah, special thanks to everyone in my lab for helping with this project. And yeah, please let me know if you have any questions.
Hello, great talk. I'm wondering if you guys did any ablations or comparisons against just like running multiple sequences through, or like running multiple structures through like protein and PNN and then averaging the output like edge embeddings before you do like autoregressive decoding without any like without like the pot stuff.
Yeah. I have some backup slides, but I don't actually know how to access them through here. But we do use tide sampling, and we show that actually tide sampling with protein MPNN does help as well. So the same, you could use protein MPNN tide sampling. It's just worse than Caliby on like generally, yeah. Oh, yeah.
This might be a simple question, but like, why did you just use a simple mean function rather than using a weighted function or something like that to compute the energy, I think, if I missed out?
Yeah, you could, so right now all we do to average the pulse parameters is like uniform weighting. You could imagine you could induce some certain weightings on specific conformations that you care about. Actually, someone from our lab is testing this kind of approach. For now, for just purely looking at designability, we just found mean averaging to be enough. But totally possible.
Hey, great talk. I was just wondering, you mentioned that the one sort of fail case that you had was a transmembrane protein, and soluble MPNN is specifically trained on like the soluble domain of proteins, right? So does Caliby also work to solubilize insoluble proteins? Have you tried this?
Oh yeah, so we offer two variants. So we offer a Caliby and then also a soluble Caliby that's trained analogously to soluble MPNN. So we did succeed on one of the transmembrane proteins, so this was using, all these designs were using soluble Caliby.
Sure, thank you.
What exactly does it mean for a sequence to have structural information embedded in it?
Yeah, so in general, these sequences that we have in our data sets, they're not just like optimized for specific structural signal. And it is kind of a, it's a kind of a hand-wavy explanation. But I guess like, even though these, one way you could kind of look at it is that some sequences are more stable than others. And so some sequences haven't been optimized for this like stability or like this clear structural signal. And so we expect that these sequences will have like kind of a less clear,
Like, does this
easy to read out.
correspond to structures with like very strong interactions where like, or, I mean like, what does it mean?
Yeah, I think it's unclear. One of the things that we're looking at is if you take design sequence profiles from either our method or even natural MSAs, and you just do a simple like POS model to do contact prediction, it's much easier to disentangle structural contacts from the design profile as opposed to natural profiles. And I think there's a lot of covariation in natural profiles, like MSA profiles that, or sorry, natural MSAs, not profiles, that don't necessarily correspond to structural contacts. And so this is sort of what I mean when I say like structural signal in a sequence.
Okay, great. Let's thank Richard again for the talk.